In the last lecture, we had examined the flow past a flat plate, and before that we had looked at the flow in a pipe. The flow past a flat plate, it is basically a surface which is parallel to the flow direction of infinitesimal thickness. Therefore, the area projected perpendicular to the flow direction is close to 0. Because of that, there is no blockage of the flow due to the presence of the plate. Okay. And due to this, most of the force that is exerted on the fluid is on the surface that is parallel to the flow. Okay. So, in this particular case, there is you have a flat plate with virtually no projected area perpendicular to the flow. Okay. You have a flat plate with virtually no area projected perpendicular to the flow. Therefore, there is very little deformation of the streamlines around the surface. You have a free stream velocity far upstream, and as the fluid goes past this plate, there is a retardation of the fluid due to the presence of the plate. So, most of the force exerted on the plate is due to the shear stress on the surface parallel to the velocity and not on the surface that is perpendicular, because that projected area is virtually 0. We have defined the Reynolds number here. The average stress, drag force divided by L into W. L is the length along the plate, W is the width in the direction perpendicular to the plane in this case, okay, perpendicular to the plane, perpendicular to the direction of the velocity, and the length is in the direction of velocity, the width is in the direction perpendicular to the velocity. And the skin friction coefficient was defined as Ft by L into W by half rho Vs square. Okay. And we had I had told you that the effect, the retardation effect of the surface, the shear stress exerted at the surface affects the velocity field within a thin boundary layer close to the surface, okay, within a thin boundary layer that is close to the surface. And this boundary layer has a thickness which increases proportional to x power half. Okay. So, the boundary layer thickness divided by x goes as the Reynolds number based upon x to the minus half. Okay. That is for a laminar flow. For a turbulent flow, it goes as a Reynolds number based upon x to the minus 1/5 power. Okay. So, these are the two these are the boundary layer thicknesses in the laminar and turbulent flow. Transition takes place at Rex is equal to 5 into 10 power 5 at a downstream distance x, where the Reynolds number based upon x, the free stream velocity, and the density and viscosity is 5 into 10 power 5. And the skin friction coefficient goes as 1 over Rex to the half, okay, when you are below transition, and it goes as 0.074 times Re power minus 1/5 when you are above transition. Okay. And based upon that, we had considered a concrete example of the flow of air past a flat plate, density 1.25 kg per meter cubed, viscosity 1.8 into 10 power minus 5 kg per meter per second. Free stream velocity is 2 meters per second. Okay. And we had calculated the downstream distance at which transition takes place, that is, the Reynolds number is 5 into 10 power 5. That came out to 3.6 meters, okay, for a free stream velocity of 2 meters a second. If your plate is 3.6 meters or larger, it will go to a turbulent flow. If it is less than that, it will be a laminar flow. The boundary layer thickness at this location turned out to be 2.5 centimeters. Okay. So, a plate of length 3.6 meters, the boundary layer thickness is only 2.5 centimeters. That means that the boundary layer thickness is less than 1/100th of the total free stream velocity. Okay. And then we had calculated the Reynolds number, the drag force for both a laminar and a turbulent flow. Okay. It calculated the drag force for both laminar and turbulent flow. Okay. In this case, the skin friction coefficient is not actually Ft, you have to multiply it by, okay, rho, okay, okay, that is the actual skin friction coefficient. Okay. So, that is the relation for the skin friction coefficient. So, here I have to multiply throughout by this whole thing into rho VFS square by 2. Okay. And then I will get, if you put in the numerical values for the viscosity 1.8 into 10 power minus 5 kg per meter per second, velocity is 2 meters per second and density is 1.25 kg per meter cubed. You will get this as 8.9 into 10 power minus 3, okay, into L to the half meters newtons per meter, I am sorry. Okay. And in this case as well, I have to multiply, okay, that is the correlation, and from that you can once again put in all the values, okay, and I have to multiply this by for the turbulent flow. So, this is laminar, this is turbulent. Laminar when the length is less than 3.6 meters and turbulent for the distance beyond 3.6 meters. Okay. And this turns out to be equal to 1.73 into 10 power minus 2 L power 4 by 5 newtons per meter. Okay. So, that is the correlation. Okay. So, kindly note that this factor has to be there in the expression for the skin friction coefficient. Okay. Now, let me proceed and discuss flow around a sphere. Okay. We had seen that for the flow in a pipe there are only two states, one is the laminar state and the other is the turbulent state. Okay. The transition takes place at a Reynolds number of about 2100. For the flow past a flat plate, once again there is a laminar state and a turbulent state. Transition takes place when the Reynolds number is about 5 into 10 power 5. Okay. For the flow in around a sphere, it turns out that the transition is more complicated in this case. Okay. You get a series of flow patterns that occur as you increase the Reynolds number. Okay. So, what is the Reynolds number? I have a sphere here, okay, and there is a free stream velocity Vfs, and this sphere has diameter d. Okay. The density is rho and the viscosity is mu. Okay. The Reynolds number in this case is defined as rho Vfs d by mu, where mu is the viscosity and rho is the density. Now, if you look at the flow pattern around a sphere, okay, the flow will go around the sphere. Okay. Okay. Because the projected area of the sphere perpendicular to the flow is substantial, the streamlines have to deform significantly in order to go around the sphere. Okay. If the Reynolds number is less than about about 1.5. These streamlines are symmetric between the upstream and the downstream hemispheres. Okay. When the Reynolds number is less than about 1.5, the streamlines are symmetric about between the upstream and the downstream hemispheres. And you have 2 points here which are called stagnation points. Okay. The left one is what is called the upstream stagnation point, and the right one is what is called the downstream stagnation point. Okay. So, you have these two stagnation points at which the fluid velocity has to be 0, and the fluid velocity goes symmetrically around this. There is symmetry between the upstream hemisphere and the downstream hemisphere. Okay. The flow around the upstream hemisphere and downstream hemisphere are both symmetric with respect to each other. This is what I will call a laminar flow, that is, as the velocity changes, the flow pattern does not change. Okay. If you change the velocity by a constant factor, then the velocity at each point in the fluid also changes by that same constant factor. That is when the Reynolds number is less than about 1.5. Okay. As you increase the Reynolds number, this upstream to downstream symmetry no longer holds. Okay. The velocity profile is asymmetric. Okay. Between the upstream and the downstream hemispheres. Okay. And this is for 1.5 less than RE less than about 24. Okay. The velocity is not symmetric anymore between the upstream and the downstream hemispheres. Okay. When you increase the Reynolds number further, what happens is the following. Okay. This is for 24 less than RE less than 400. Okay. In this case, what you find is that there is what is called a separation bubble. Okay, consisting of closed streamlines which forms at the rear end. That is, the fluid velocity that is coming from the upstream side does not go all the way around the sphere. Rather, there is a separation bubble which consists of constantly recirculating fluid on the downstream side. Okay. And the velocity that is coming from the upstream side goes around the separation bubble. Okay. So, this is the formation of a separation bubble, okay, on the downstream side. Okay. This is what is called an attached separation bubble. Okay. So, effectively the shape of the flow around the sphere is not the shape of the sphere itself, but rather the shape of the flow around the sphere consists of the sphere on the upstream side plus the separation bubble. Okay. Okay, so, the fluid is going around the separation bubble in this case. Okay. This happens when the Reynolds number is between about 20 and 400, okay. Sorry, 24 and 400. Okay. What happens when you increase the Reynolds number even further? Okay. In this case, okay, you have what is called flow detachment on the rear side. Okay. So, you have these periodic shedding of vortices. Okay. Okay. And the flow from the upstream side goes around these vortices. Okay. Okay. The flow never comes all the way around to the center line. Okay. The flow from the upstream side never comes all the way down to the center line, and you have what is called periodic vortex shedding. Okay. And this region is called the wake. Okay. There is effectively vortex shedding in the wake. Okay. And this happens when the Reynolds number is approximately between 400 less than about 4000. Okay. So, there is regular vortex shedding in the wake at the rear. Okay. So, the flow is no longer steady, you have a periodic variation in the velocity field within the wake region. Okay. So, this happens when the Reynolds number is between 400 and 4000. Okay. Next, when the Reynolds number further increases, when the Reynolds number further increases, there is a more and more regular wake that is formed. Okay. This wake extends slightly upstream of the mid plane of the sphere. Okay. So, the flow goes around this wake from the upstream side, okay. And within this you have a turbulent wake. Okay. You have a turbulence in the wake. It is no longer a regular vortex shedding like you had up to 4000, but rather it is irregular, okay, a turbulent wake. Okay. This happens for 4000 about 2 into 10 power 5, okay, for Reynolds number in that range. Okay. And then when the Reynolds number increases beyond 2 into 10 power 5, okay. This wake attachment point, which is slightly upstream, okay, of the mid plane, okay, this wake attachment point which is slightly upstream of the mid plane suddenly shifts to the downstream side. Okay. Okay. And you get a wake that looks like this. Okay. There is turbulence in the wake, okay, and also there is a turbulent boundary layer on the upstream side. Okay. That is, the flow in the boundary layer on the upstream side also becomes turbulent. Okay. Okay, this also becomes turbulent, okay, for 2 into 10 power 5 less than Re. Okay, when Reynolds number exceeds 2 into 10 power 5, you get turbulence both in the boundary layer and in the wake. Okay. In this case, when it is less than 2 into 10 power 5, the flow in the boundary layer on the upstream side is laminar, okay, for this and below lower values. There is a boundary layer in the upstream side where viscous effects are important, and there is a wake on the downstream side. The flow in the boundary layer is laminar, whereas when you go to 2 into 10 power 5, the wake shifts to the downstream hemisphere, and the flow becomes turbulent in the boundary layer as well. Okay. So, these are the transitions that take place as you increase the Reynolds number. Okay. So, let us consider what are the drag coefficients, okay, in the different Reynolds number regimes. Okay. Recall that the drag coefficient is defined as Fd by Ap, the projected area perpendicular to the flow. Projected area perpendicular to the flow is pi d square by 4. Right. The area of the circle perpendicular to the flow is going to be equal to pi d square by 4, okay, divided by half rho free stream velocity square. Okay. So, that is the drag coefficient. Okay. Let us look at what the drag coefficient is in the different regimes. Okay. First of all, for Re less than about 1.5, flow is laminar. The inertial effects can be neglected compared to the viscous effects, which means that the drag force should depend only upon viscous effects. Okay. The density should no longer be a parameter. Okay. That means that the drag force just from dimensional analysis has to be proportional to the viscosity into the free stream velocity into d. Okay. You can easily verify that this has dimensions of force, okay, just from dimensional analysis, which means that CD, which is equal to Ft by pi d square by 4 by half rho Vfs square. Okay. Half rho Vfs square. This has to be equal to mu Vfs d, okay, or it has to be proportional to, okay, by pi d square by 4 divided by half rho Vfs square. Okay. And you can cancel one velocity in the numerator and denominator as well as one factor of diameter, and you will verify that this is proportional to mu by rho Vfs d, okay, which is, okay, it's basically 1 over the Reynolds number. Okay. So, the drag coefficient has to be proportional to 1 over the Reynolds number in the low Reynolds number regime. Okay. A detailed calculation will show you that the constant is actually 24 by Re. The constant is actually 24 by Re in the low Reynolds number regime. Okay. So, in this particular case, for low Reynolds number, the drag coefficient is equal to 24 by Re. Okay. Now, as you increase the Reynolds number, the effects of inertia become important. Okay. Now, you can calculate the drag coefficient up to about 400 or so. Okay. So, in this regime, okay, for both up to 400 and 24 to 400 and 1.5 to 24, okay, we can use a correlation. Okay. So, this is for Re less than about 24, sorry, 1.5. Okay. Once Re becomes greater than 1.5, the flow is no longer dominated only by viscosity. Inertial effects become important, and you have to correct the drag coefficient for these inertial effects. Okay. A correlation for the drag coefficient of the form 24 by Re into 1 plus 0.15 Re power 0.687. Okay. That accurately captures the drag force. This is an empirical correlation, whereas for Re less than 1.5 it is an analytical calculation. In this case, it is an empirical calculation fitted to experimental data, this correlation. Okay. This works for 1.5 less than Re, okay, about 400. Okay. So, this is almost identical to the first result that we get. Okay, it comes out of, okay, this is basically Stokes' drag law. Okay. Recall that we had derived this in the limit of low Reynolds number when using dimensional analysis up to within a multiplicative constant. that constant was 3 pi if you recall. Okay. That constant was 3 pi, okay, if you recall, okay, in the viscous limit, and if you substitute that you will get 24 by Re, okay, here. This is almost the same except that it has this inertial correction, okay, and this is called the Schiller-Naumann correlation. Okay, this is called the Schiller-Naumann correlation. Okay. This works up to a Reynolds number of about 400 or so, okay, or it works reasonably well to a Reynolds number of about 400. Okay. In the region between 400 and 2000, okay, the drag coefficient, okay, CD is approximately 0.4. Okay. CD is approximately 0.4 for 4000 between Re less than or equal to 2 into 10 power 5. Okay. And at this point you have a sudden drop in the drag coefficient. Okay. So, if I plot on a log plot, okay, the natural logarithm of Reynolds number on the x axis and the natural logarithm of CD on the y axis, we know that it has to have a slope of -1. CD is equal to 24 by Re, which means log CD is equal to log 24 minus log Re. Okay. So, this will be CD is equal to 24 by Re. Okay. Okay. It works up to about 1.5. Okay. Beyond that it takes a turn like this. Okay. So, this will be about 24. Takes a turn, okay, and between about 4000 and 2 into 10 power 5 it goes to almost a constant value. Okay. That constant value is approximately equal to 0.4. Okay. That constant value is approximately equal to 0.4. Okay. So, if I extend this back here, this will be 0.4 CD equals. CD equal to 0.4, and then at 2 into 10 power 5 there is what is called a drag crisis, okay, which occurs, as I told you, because the two stagnation points, I am sorry, the two attachment points here shift suddenly to the downstream side from the upstream side. Okay. And when they shift to the downstream side, the effective low pressure region at the rear end is smaller, and because of that you have lesser drag force acting on the sphere. Okay. And this point is where it is called a drag crisis. A sudden decrease in the drag force as the Reynolds number is increased. Okay. And the Schiller-Naumann correlation gets, so this will be the Stokes loss 24 by Re, and the Schiller-Naumann correlation actually gets it correct up to about this point. Okay. Up to about 400 the Schiller-Naumann correlation is accurate. Between 400 and 4000 there is still a slight decrease. After about 4000 it saturates at about 0.4, and then at 2 into 10 power 5 there is a drag crisis. So, this is the log plot of the drag coefficient versus the Reynolds number showing the different regimes. Okay. This is basically a viscous regime. Okay. From here to here there is viscosity, but there is also an inertial correction given by the Schiller-Naumann correlation between about 1.5 and 400. Between 4000 and 2 into 10 power 5 it is almost a constant, and then there is a drag crisis which decreases the drag coefficient. Okay. So, this in summary is the qualitative nature of the flow past a sphere as the Reynolds number is increased. Reynolds number based upon the free stream velocity, the diameter of the sphere. Low Reynolds number, there are two stagnation points. The velocity profile is symmetric between the upstream and the downstream hemispheres. For Reynolds number less than about 1.5, the drag coefficient is 24 by Re. Okay. 1.5 to 24, there is asymmetry between the upstream and the downstream sides, okay. But you still have two stagnation points, one on the upstream and one on the downstream side. Okay. And in this case, there is an inertial correction to the drag force. CD is equal to 24 by Re 1 plus 0.15 Re power 0.687. Okay. There is a correction due to inertia for this drag force, okay, because inertial effects become significant, and that correction also carries through to this case where you have a separation bubble forming at the rear. Okay. So, here also you have the same drag coefficient, drag correlation, empirical drag correlation, okay, for 24 to 400. So, this empirical correlation holds all the way from 24 to about 400. When it goes beyond 400, you have unsteady flow in the wake, periodic vortex shedding. Okay. So, the flow is no longer steady. Reynolds number is further increased, that unsteady flow becomes turbulent. Okay. And in this region, the drag coefficient is equal to 0.4, okay, approximately equal to 0.4. Okay. And then at 2 into 10 power 5, a transition takes place where the flow in the boundary layer on the upstream side also becomes turbulent. Okay. And at beyond 2 into 10 power 5, you have a drag crisis where the drag force decreases discontinuously. Okay. So, these are the characteristics of the flow past a sphere. Okay. So, in the next lecture, I will briefly discuss this and then solve a problem on how we can use this in order to find out the velocity and the diameter for different regimes for a particle settling in a fluid. Okay. I will continue this in the next lecture. I will see you then.